And there will be like whole bunches of homework problems that we'll be doing on Monday. Arrgh. So nothing due today, but a few things due on Monday. So we'll pick up where we left off. I almost, you can go back. This one? That's good.
Sure.
Or back more?
That's fine.
Well, this is good because this kind of gets it all, puts into context what we need to be talking about. We talked about the mass of a mole, otherwise called a molar mass. And for elements, it's pretty easy. It's the decimal number. For compounds, before this, actually leading up to this, we did calculate some molar masses of compounds. And we said that you basically either calculate the molecular weight for a molecular compound or the formula weight for an ionic compound, and instead of AMUs, it's grams per mole. Okay, so that's kind of how we left it. Okay, so then we went ahead and did a mass to moles conversion. Now, I'm not about memorizing things. Sometimes teachers will say, anytime you see grams and you're trying to get to moles, then use the molar mass this way. I simply just come up with the molar mass and either use it as it is or use the flipped version to get, in this case, from grams to moles. So one of the things I tried to emphasize on Monday was anytime you're doing this sort of problem, you need to show all of your work. So we're going to need the molar mass of CHCl3. So we use the decimal number for carbon, takes it times 1, decimal number for hydrogen times 1, decimal number for chlorine times 3. You must show this, and you must include units. So then we said if you're going to go from grams to moles, the first term is going to be your units you want to convert, grams over 1. In this case, we're going to use the flipped version of the molar mass so that actually grams will cancel. We're left with units and moles. And we're going to round to 3 sig figs. Okay. Now, in this case, notice I didn't say what 0.0107 moles of CHCl3. I could have. But just the fact we're dealing with one species, actually, this kind of works just fine. Okay, and that's today's. Is that good? I don't know. It's okay. You know where I live.
Yeah.
So now this is a different compound. It's methane. And this is a moles to mass problem. Sometimes I just focus on the units and where the question is and where the given number is. So we have 0.444444 moles, and we want to get to grams. So again, you have to show this work. This right here is knocking out the molar mass of methane, which is almost as fun to say as the molar mass of magnesium. So you're going to take 1 times 12.01 plus 4 times 1.008, and you're going to round to 2 decimals. Okay, remember this is like one of the few things that the numbers 1 and 4 are exact. Okay, they don't bring any uncertainty, so basically you're adding a bunch of numbers, and when you're adding, you round according to decimals. So that is what we're going to use. Our first term is going to be that 0.4444 moles over 1. And now we want moles to cancel, so we're going to use the unflipped version of the molar mass, which is simply that 16.04 grams over 1 mole. I should never see, in this class anyway, I should never see a term inserted. I'll show you what I'm trying to say. I should never see without what I call unpacking it. For instance, I would be very doubtful if I saw, instead of 16.04 grams per 1 mole, if I saw 16.04 grams / mole. I would be very suspicious if it was lit. So we're going to round according to 4 significant figures. So the mass of CH4 is 7.129 grams. Okay, not too bad. I wish they were all kind of that straightforward. Okay.
I did not get one.
I got 1228.
Ah, direct. 4 times me too. I know. Good job. Wonder what happens. I don't think it would make a difference. 12.01 times, excuse me, 12.01 plus 4 times 1.008. And then take that times 0.4444. Aha.
That's what it is.
So I would accept either one.
The unrounded 16.0.
Yeah.
whatever. Okay.
Either one's great. I probably, if I was just doing it, I probably would come up with the same number that you guys did. So what I tried to say is that actually, if you use the unrounded version of that there, then you get the 7.129. Okay? That's where I get to catch you on the other side. A lot of times when I'm grading, if your work looks great, and your answer's close, I'm like, okay, it works for me. Now you know one of my secrets. Okay. So now this one looks like the same sort of problem, but it's a little bit different. You see clearly we have 1.92 grams. Okay, so grams to something, and you see the word moles. But in this case, we're going to moles of bromine atoms, otherwise known as bratoms, instead of moles of the compound. Okay? So in order to work this, the little twist is to recognize that when you're given the formula CBr4, carbon tetrabromide, okay, what it really means is for one molecule of CBr4, you have 4 bromine atoms and 1 carbon atom. That's the formula. Well, we could scale that up in terms of moles, and that means in 1 mole of CBr4 molecules, you have 4 moles of bromine atoms and 1 mole of copper, 1 mole of carbon atoms. Okay? So anytime you could actually take the word and put an equal sign there. Okay? For this particular compound, 4 moles of bromine equals 1 mole of carbon. And anytime you have an equality like that, you can make it into a conversion factor. So here in a minute, when we work this mass of CBr4 to moles of bromine atoms, we're going to do it like normal and come up with moles of CBr4, but then we are going to insert that ratio to get our moles of CBr4 to cancel and be left with moles of bromine. So here we go. Bless you. So like I said, we're going to work it. We're going to go from mass of CBr4 to moles of CBr4, and then we're going to do one last step to get to moles of bromine atoms. So you have to show this works. So the molar mass of CBr4 is 1 times 12.01 plus 4 times 79.90, rounded to 2 decimals. It's 331.61 grams per mole for the compound. 331.61 grams per mole. That's pretty heavy stuff. Anytime you start adding, like, bromine, it's pretty heavy. Iodine, even heavier, right? It gets heavy quickly. So let's work this problem. So the first term is going to be the mass of the CBr4 that was given, 1.92 grams of CBr4 over 1. And since we want grams to cancel, we're going to use what? The flipped version of the molar mass. So the next term is going to be 1 mole CBr4 over 331.61 grams CBr4. Now this is different. I am going ahead and being what I say explicit. I'm adding information. I'm putting the CBr4 there on purpose because the last thing I need to do now is to go from moles of CBr4 to moles of bromine atoms. So at this point, what we have canceling, we have grams of CBr4, canceling grams of CBr4. We're left with moles of CBr4. So now we insert that ratio you saw on the previous slide. Now we insert 4 moles of bromine atoms, 4 moles of bromine for 1 mole of CBr4. So now grams of CBr4 cancel, moles of CBr4 cancel, and we're left with moles of bromine atoms, which is perfect. So don't forget to round it correctly. On your test tomorrow, I may not be so picky about the last digit, but I will be picky about rounding. So to me, it's looking like 3 significant figures, and that's the limiting term there. There's no uncertainty brought by that 1, or that 4, or that 1. And actually, there would be uncertainty brought by, or there is uncertainty brought by the 331.61, but there's 5 there. Okay, so I am limited to 3 because of this. All right, so 3 sig figs, I got 0.0232 moles bromine. And sorry, I like it when you guys check it, actually. Did you check it, Cameron?
Yep.
All right, keep me posted. So remember how significant figures go then is, oops. This digit is not significant. It's important, but it's not significant. So we do have 3 sig figs there. All right. Already good. We have all sorts of brain teasers then. These will be due Monday, right? You have the big long weekend to transition from Unit 1 to Unit 2. So let's take a look at those right quick. Maybe. Yay, I win. Okay. So there's 4 problems here. It gives you the formula for amino acid methionine, okay, C5H11 and O2S. And the first one is determine its molecular mass. Now remember, molecular mass will be in, that's different than molar mass. Kind of let's all get our bearings there. I had to pause. Molecular mass, the mass of a molecule, that's going to be in AMUs, so units of use. B, I have a hint here. Some of these, I know you guys don't not need a hint, but I go ahead and I put something down usually. Okay? So hint for B is pretty much giving it to you. Because of the formula of the compound, it says what are the number of moles of hydrogen atoms in 1 mole of the compound? Well, it's 11, right? Because the subscript's 11. So there's the answer to B. I could make it any sneakier. All right, C says how many grams of carbon are there in 1 mole of the compound? So this is where I kind of do it this way. You go from moles of the substance to moles of carbon. There's 5 moles of carbon in 1 mole of the compound, right? That's going to go right there. I guess I didn't. I'm sure, okay. 5 moles. C is equal to 1 mole of compound. Okay, that goes right there. And then once you have moles of carbon, you can get to grams of carbon using the molar mass of carbon, which is 12.01 grams per mole. Okay, that's the way I would do it. There's more than one way to skin most of these. Okay, that's your hint. Take it or leave it. For the last one here, what are the number of carbon atoms if you have 9.07 moles? Okay, so, oh yeah, I was like, really? So now we don't want, notice that you can go from moles of the compound to moles of carbon simply knowing that there's 5 moles of carbon for every mole of compound. That's pretty easy. But it says how many carbon atoms are there. Don't let this throw you off. It doesn't say how many moles of carbon, how many individual carbon atoms. So this is an example where you need to go from moles of carbon atoms to counted individual atoms using Avogadro's number. 1 mole is equal to 6.022 times 10 to the 23rd. So There's a lot of, that's almost a, sometimes you read chemistry problems and you're like, were you trying to trick me, right? So for this one, we're switching gears. Of course, bromine is one of those diatomic elements. And so we have Br2 molecules, and then we have Br atoms, right? So determine the number of moles of Br2 in A, B, C, and D. So in A, it gives you Br2 molecules. So it's not too bad. Go from those molecules to moles of bromine using Avogadro's number. In the next one, oops, I didn't have builds here. In B, they give you individual bromine atoms. So if they give you individual bromine atoms, okay, I can do this though. If they give you individual bromine atoms, you can get to bromine molecules by recognizing there's 2 Br atoms in one molecule. That's not too bad. Then once you, to get to moles of bromine, you need to use Avogadro's number again. For C, where did my thing go? For C, it looks like this. They give you the mass of bromine, and you need to calculate the molar mass of Br2. Now here's where students are like, what's the molar mass of Br2? It's 2 times whatever 1 Br is. We'll show it, okay? I know it's like, really? Yeah. So use the, show me calculating the molar mass of Br2, and then go from mass of Br2 to moles of Br2. The last one actually has you bring in something else we learned, a few other things, or maybe one other thing we learned this semester, or so far in this class. Of course, this letter here, this is density. So we can, you're given the volume of Br2, okay, and the density of Br2. We can get to the grams of Br2 using density from volume. And once we have the grams, we can use the molar mass of Br2 that we used in C to get to moles of Br2. So again, whether you use these hints or don't use them, or try to do it without and then look, or look afterwards, that's kind of all up to you. The third one looks like this. And for A, I kind of reminded you, show all of your work. Determine the number of moles of an assortment of things in an assortment of things. So for the first one, you're given grams of the compound, and you're supposed to come up with moles. Use the molar mass of the compound. Okay, that's a mass to moles problem, pretty straightforward. For B, they want individual nitrogen atoms. So you're probably going to have to use Avogadro's number, aren't you? So for B, they want individual nitrogen atoms in a certain mass of magnesium nitrate. So, of course, you can go from grams of the compound to moles of the compound, and then recognize, using the molar mass, and then recognize that the subscript for nitrogen is actually 2. Okay, so then you can go from moles of the compound to moles of nitrogen. For C, you're after this one. I sat in my desk and I was having a brain fart, so I had to like concentrate and concentrate. I hate it when they give you 2 substances, okay? But basically, if you read it a few times, it kind of looks like this, okay? Where they give you the mass of the C6 compound, okay? You can go to moles of that compound using its molar mass. Then we can go to moles of oxygen using the fact there are 6 moles of oxygen per compound. Okay, that will give us moles of oxygen in the compound. Now, it says basically I want to know something else about the other compound where you have the same number of moles of oxygen in both compounds. So right here at this juncture, when I'm switching compounds from the C6 compound to the C7 compound, I pull in that I want 1 mole of each. Then once you have moles of oxygen in your other compound, you can backtrack to moles of regular old moles of the C7 compound, recognizing that there are 6 moles of oxygen, okay, in 1 mole of this compound. That will give you moles of the compound. Then you can go to moles of nitrogen, recognizing there are 3 moles of nitrogen for every 1 mole of compound. Then you want nitrogen atoms, so then you're going to have to use Avogadro's number. So that's your hint for that one. All right, The last one, determine the mass of, given that moles of P4. Of course, you show me you're calculating the molar mass of P4 and then use it to go from moles to grams. For B, they give you the molecules of compound and you're supposed to tell me what mass that would be. So of course, in this case, you're going to go from molecules of stearic acid to moles of stearic acid using Avogadro's number. Then you can go to grams using the molar mass of stearic acid. My hint there was make sure you show all of your work. For C, they give you the moles of nitrogen atoms, and they want to know the mass of this amino acid. So you can go from moles of nitrogen atom to moles of lysine, recognizing, I did it in purple up there, that there's 2 moles of nitrogen atoms for every 1 mole of compound to get the moles of lysine. Then you come up with the molar mass of lysine, and then you go from moles of compound to grams of compound. And that's it. They're all kind of fun. They're all like little brain teasers. Okay? I know, hurts my brain. Okay, so back to finish up this part. So, do you remember the other day, and I'm not going to add to it because we'll add to it later, where we had molecular compounds and ionic compounds, okay, going on? So ionic compounds are sometimes just generally called salts. So table salt is an ionic compound, but a lot of times any ionic compound is generally called a salt. You know you have an ionic compound in general if you have a metal in your formula. So look for the metal. So ionic compounds or salts, one of the things that they do is sometimes just in their natural state, they will pick up waters of hydration. They'll run around they just prefer to be hydrated. And I'm going to show you kind of a few pictures I got off the internet of what hydrated salts kind of look like, just kind of their formulas. But they aren't really a chemical bond, these little links between the salt and the waters of hydration. But the important thing about waters of hydration is they can be driven off just simply by heat. You just heat up a hydrated salt and you drive off the waters of hydration. That's important. Okay, so they're kind of different. So for instance, barium chloride, the natural waters of hydration that gravitate around every BaCl2 formula unit is 2. Okay, so barium chloride has 2 waters of hydration. Okay, barium chloride dihydrate. Copper 2 sulfate has 5 waters of hydration. Copper 2 sulfate pentahydrate. It's just what it does. Can you get regular copper 2 sulfate without 5 waters of hydration? Yes. And then the last example I have up here is iron 3 nitrate. Iron 3 nitrate, for every formula unit of iron 3 nitrate in a crystalline lattice structure, it will have 9 waters of hydration. Kind of, I'll show you in a minute what that looks like. Kind of encircling it. See if this works for you. I tell you that actually you can take these salts and heat them up and drive off those waters of hydration. Okay, if you do that, you end up with something that is what we call anhydrous. Anhydrous, the anhydrous salt. Anhydrous means without water. So, here we go. Here's my little pictures from the internet. So you see the barium chloride on the left, 2 waters of hydration. In the middle, we have the copper 2 sulfate. This one I was looking at my office, I'm like, now how does that work? So actually, here's your SO4, 2 minus, and here's your copper 2. So there would be a ... a chemical bond, ionic chemical bond, but then your waters of hydration, your 5 waters of hydration kind of orient themselves that way. Now, if you stay in chemistry, I mean, it is no small thing how these waters of hydration are oriented. They are players in how that hydrated salt will behave. Okay. Then the last one, there are actually 9 waters of hydration here. Oh, one of the things I didn't say yet is that, let me go back. Like, if I was going to say this formula right here, I would say BaCl2 dot 2H2O. The next one, CuSO4 dot 5H2O. I just use the word dot to basically say what's following it, our water's hydration. Okay. So, on to the problem. So here we go. And actually I went ahead and I have like a little slide to show you that I'll push out there. But I told you that waters of hydration can be driven off, and actually that's what this problem's about. If you read it a few times, it says that you have a copper 2 sulfate, and you don't know how many waters of hydration attach themselves per 1 unit of copper 2 sulfate. So you're supposed to find that out. And then what happens is they go ahead and they weigh it before they heat it, and they weigh it after they heat it. Notice after they heat it, they lose weight. What's weight is lost? The waters of hydration. So in order to find X, this is the sort of thing, the sort of approach you go about. Okay? So there's this one actually lends itself almost, I think, to a drawing. So again, sometimes my doodles are just stalling, and sometimes they really are to do something. So there's my hydrated salt. I don't know the numbers of waters of hydration. I heat it up, and I get a blob back, and I drive off waters of hydration. Okay? That's kind of what we have going on here. The mass of the anhydrous, copper 2 sulfate, was given, so you're going to want to know what the word anhydrous means. It means without its waters of hydration. That mass was given. Then, of course, we can get the mass of the waters by difference. I didn't do it here, but we're going to do it here in a minute. We get the mass of the waters by difference. So we basically have the mass of the anhydrous salt and the mass of the water. So we can get the moles of the salt by using the molar mass of the salt. We can get moles. We can get the moles of the water by using the molar mass of water. Then kind of the last step in this sort of problem is to simply do a ratio. If we go about taking the moles of water divided by the moles of copper 2 sulfate, moles of water for every 1 mole of copper 2 sulfate, by golly, we have come up with what X is, the number of waters of hydration per mole of salt. So that's kind of exactly, in a nutshell, what we're going to do here. Okay. So we'll need the molar mass of both water and copper 2 sulfate. So copper 2 sulfate molar mass is 1 times 63.55 plus 1 times 32.07 plus 4 times 16.00. The salt's molar mass is 159.62 grams per mole. The molar mass of water, which you're going to be dealing a lot with in this class, is 2 times 1.008 plus 1 times 16.00. So the molar mass of water is 18.02 grams per mole. So in the strategy I showed you, basically we're going to use these two molar masses to come up with the moles of the salt and the moles of the water. Have I already said that? I think I have. To show all your work, part of it is actually if you make a little mistake, like transpose a number, which I haven't been known to do before, then actually I can see in your work what happened. And that makes it a lot easier to go ahead and give you, a significant credit. Have you ever heard somebody survive college on partial credit? That's showing your work and be able to BS, But actually, I'm pretty good at seeing through BS. But okay. So the mass of the water we get by difference. So we take the mass of the hydrated salt, 1.023 grams, minus 0.654 grams. So the mass of the water is 0.369 grams. So then we have two molar mass problems, grams to moles problem. Let's start with the water. So we're going to take that 0.369 grams over 1. And we want grams to cancel, so the next term is going to be 1 mole over 18.02 grams, the molar mass of water. Grams will cancel. We'll be left with units of moles, and rounded to 3 significant figures, the moles of water are 0.0205 moles H2O. But this is a good example where, see the blue? The blues right there, on the slide, those are my titles. They're the title of the little, it's kind of like when you guys hand in your calculations for your, it's the title of what I'm going to do. And since I did that, I don't have to like put grams of H2O. I could. It's certainly not bad. But the fact that I labeled it means that I can get by without putting all of that other stuff. So actually it's a time saver. So the next one, the moles of the salt, we take the moles of that was left over, the residue, so 0.654 grams over 1. And then we want grams to cancel, so we're going to flip the molar mass of the salt. 1 mole times 1 mole over 159.62 grams. There's the molar mass. So grams of the compound cancel. We're left with units of moles. Rounded to 3 significant figures, I get 0.00410 moles of salt. So this is a good example in chemistry, and actually one of your homework problems for Monday, you're going to do this, in that we just kind of randomly took the hydrated salt, the original thing that we put through the furnace. And that was our basis, and based upon that we got a certain mass of salt and a certain mass of water was driven off. That was our basis. So the last step then, we just need to take the moles of H2O divided by the moles of CuSO4. Again, if you've labeled your problem as you've gone along, this can be easier. So that's 0.0205 moles H2O, and I will be explicit here, divided by 0.00410 moles of CuSO4. And hopefully it's kind of a roundish number. If you get something like 2.6, then probably either somebody gave you bogus data or you did something wrong. It should be kind of a nice whole number. And I'm going to grab my calculator, but here I have to 3 significant figures, 5.00. And what does that mean? Well, if you look at the labels in your problem, that means 5.00 moles H2O per 1 mole of CuSO4. And by definition, those are the number of waters of hydration, okay, that will show up after the dot. So just based upon that analysis, we can go ahead and say what the formula for this hydrated salt is. It's CuSO4 dot 5 H2O, 5 waters of hydration. And we'll talk more about chemical formulas being either molecular formulas or empirical formulas down the road, but the empirical formula. All right. So these are also done. But wait, there's good news. See the question number 73? Go ahead and mark that off, and that actually snuck in there kind of early. So just do 22, Chapter 3, 22, 71, and 74. So let's take a look at those right quick. Okay. So 22 is not really a hydrated salt problem. Well, it is, but it is. I guess it is. 22 is more like a weight percent problem.
Oh.
I know. 22 says that you have chromium-3 nitrate and you have 9 waters of hydration. And this is where I would say set your basis. This is what I mean. You're supposed to come up with, of that one repeating unit, how much of the mass is brought by those 9 waters of hydration. So my suggestion is to do something, again, like this is kind of a theme for working chemistry problems sometimes. You set the basis, and my suggested basis is 1 mole of the compound, the hydrated compound. You can come up with the mass of, in 1 mole of the compound, the mass of water will be 9 times the mass of 1 water. In 1 mole of compound, the mass of the compound will be, the hydrated compound will be, whatever the periodic table says that would be, adding them all up together. Okay, that's my hint for that one. That's hard to give a hint for.
So in order to find out the mass of the hydrate there, would we add all of that together?
Mm-hmm.
Okay.
Yep. So,
So it'll be like the molar mass of CrNO3
Yep.
plus the molar mass of 9H2O.
yep,
Okay.
the whole thing,
That's
that
what
mass
the
is gonna
mass
go
of
in the
that is.
bottom.
Cool.
And the top is gonna be actually these 9
Just-
waters of
yep.
hydration. 9 waters of hydration per 1 of your hydrated salt units. And then, of course, if you stop there, you'll end up with something called mass fraction. To get it parts per 100, multiply it by 100%. The next one is, it's kind of different. It threw me off. I was getting ready to kind of show it to you guys. Notice in this case, they're actually using copper 2 sulfate as a desiccant. If desiccators are kind of like little things with little stuff at the bottom. When you get these little pillow things that say "do not eat in your purse" or whatever, that's what it is. It's like a desiccant. It's supposed to absorb water. Okay, why does it do it? Well, because it prefers being hydrated. Okay, so they're using this in gasoline, taking copper 2 sulfate and putting it in their gasoline to try to draw out the water. And copper 2 sulfate likes to have 5 waters of hydration. Then the problem goes on to say, what if I want to remove 12.6 grams of hydration? Okay. The question is, what mass of the anhydrous salt do I need to have there? Okay, so you might already, if you don't know how to work this problem, if you kind of diagram it, you're like, well, what do I know? Well, you know the mass of the water. Well, from the mass of the water, can I get to moles of water? Yeah. Okay. From moles of water, can I go ahead and get to moles of copper 2 sulfate? Yes, you can. 5 moles of water of hydration for every 1 mole of the anhydrous salt. Okay, just from the formula for the hydrated salt. So here's your hints. I would use the the mass of the water to get the moles of water. I would get to moles of copper 2 sulfate from moles of the water using the 5 waters of hydration for every 1 mole of copper 2 sulfate. Then once I had the moles of copper 2 sulfate, I would get to grams of copper 2 sulfate using its molar mass. And these hints are kind of different than I'm used to giving them to you, but there's your hints. And then the last one looks like this. It's exactly like what we were in class. You're given the mass of hydrated salt, but you don't know how many waters of hydration there are. You're given the mass of the anhydrous salt, okay, and by difference you can find the mass of the water. It's exactly like we did before. Okay, so we can get the moles of water and the moles of magnesium sulfate. Okay, go ahead and then take a ratio, and that will be our X, just like we did in class. Smiley faces all around. Okay, I think that's it. Yeah. So I'll throw those out there. Again, those will be due on Monday. Now, about your labs,